We now look at another kind of a test called Goldfield-Kohn test, and this test can be used if the error term in the regression is normally distributed, and it follows all other classical linear regression model assumptions other than, of course, the heteroscedasticity. So what we try to really do here is we try to basically test this kind of a problem, which is that is your variance or the standard deviation of this regression model is a increasing or a decreasing function of the regressor. Okay. So what is the method? The method is that you first arrange n observations in the sample in ascending order, and this is when I say observation in sense that we're talking in terms of xi's. So let's say if this xi is given to me and I assume that there are like n observations. So what I'll do is I'll split the sample into three sets. So let's say that so this 3 by 8, the first 3 by 8 over here, I'll call this um, n prime. Okay, another 3 by 8 here, I'll call them n prime. So basically we have taken n prime. So the bottom n prime is basically the represent 3/8 of the sample. Likewise, the top n prime represent the top 3/8 of the sample. So 3 by 8, 3 by 8. Now we have in between the middle observation, the middle observations. Okay, and the middle observations are basically equal n minus 2n prime. And we drop these observations, we drop the middle observations, we drop them, and what we do is we run separate regressions for the first n prime and the bottom n prime, and when we run these two regressions on this particular sample, let me just change the pen color. When I run regression for this sample and this sample, I'll get the residual sum of squares from both of them. So I'll get RSS here as well. I'll call this RSS1. I'll get residual sum of squares from the bottom n prime. So I'll call this RSS2. Now the idea is that in this test we assume that the variance increases in x, which means RSS2 is hypothesized to be greater than RSS1. So we can define the null hypothesis as RSS1 is equal to RSS2. That is, there is no problem of homoscedasticity. That is, there is no homoscedasticity. Oh, there's a typo here. So I have made a small correction here. It should be no heteroscedasticity. So basically what we are saying is that in the null hypothesis that there, so the errors are homoscedastic or there is no heteroscedasticity problem. Okay. So basically in such a situation, RSS1 will be equal to RSS2. The alternate, of course, H0 is not true. So we then construct a F statistic, which basically is RSS2 over degrees of freedom, RSS2 over degrees of freedom. And so in this case, let's say if there is only one explanatory variable, so this will be basically n prime minus 1, and same here as well, n prime minus 1. Okay, and what we do is we so basically we construct this F statistic, and we look for the critical value. If the F statistic exceeds the critical value, then we reject the null hypothesis, which is that of homoscedasticity, and then we say that yes, there indeed exists some heteroscedasticity, or in other words, the RSS2 is greater than RSS1. Just a small correction, this should be basically n prime minus k here, where k is a number of parameters to be estimated. So in this case, if we are running a simple linear regression and we are estimating two parameters, the intercept and the slope, this will become basically n prime minus 2 in both the cases. Okay.